further ado, Melissa is our next speaker, Melissa Roth. She is one of the founders and lead researchers at Off-Planet Research, a space research and development company in Lacey, Washington. She's excited about the renewed push to return to the moon in a long-term, sustainable way that will be enabled by ISRU, groundbreaking technology, and international interdisciplinary collaboration. Off-Planet Research simulates extraterrestrial environments and manufactures planetary regolith. I'm not familiar with this word. Maybe you can touch on it.
Definitely.
Regolith stimulants for testing landers, rovers, and landed technologies. They also help organizations develop methods of extracting resources like oxygen and water from the soil and on other worlds, or study how to grow food on the moon to feed and support people who will live and work in space. Please welcome Melissa Roth.
Well, thank you for that. And I might breeze over a few of those points again. And don't worry, we'll talk about regolith. That's actually the point of the whole presentation. So thank you again. My name is Melissa Roth, and I am one of the founders and lead researchers at Off-Planet Research located in Washington. And I want to thank the Blue Marble Conference for having me today. I'll be speaking about lunar regolith, the challenges that it presents to human and robotic missions, and how lunar regolith and resources within it can be leveraged to help sustain a long-term presence on the moon and in deeper space. Off-planet research simulates extraterrestrial environments for testing spacecraft and landed technology, with a current focus on the lunar environment. As engineers, we know testing and good testing materials are important for increasing mission assurance, cost effectiveness, and to speed the development of space-based technologies. OPR was founded in 2015, and we spent several years developing our lunar regolith simulant production methods to make sure we mimic the natural formation processes on the moon, as most commercial crushing methods tend to smooth the particles or contribute high levels of contamination. We have also developed lunar icy regolith simulants that include the 9 components found in the L-Cross plume, and are expanding this work under a NSF SBIR grant. In addition to consulting and working with lunar regolith simulants and conducting component testing, we are also developing our own technologies such as self-cleaning dust-proof fluid and gas connectors through a NASA SBIR grant. We are a small company looking to grow and expand as landed technology and processes are developed and need to undergo relevant and representative testing. After spending many years and millions or billions of dollars to develop and launch, we want to help organizations ensure the technology performs as expected and is able to complete a successful mission or long-term operation. It is our goal to help a broad range of missions and research, from small research-based and research-backed experiments to private organizations' technology to government-led expeditions. We feel that this approach will allow us more long-term stability and reduce the uncertainty of specific missions or technologies that have affected the space industry for decades, as we've heard a couple of times now. So to clarify some terminology, regolith is a geology term referring to the layer of unconsolidated rocky material covering bedrock and is used to describe the soil on the moon and other planetary bodies. Lunar regolith simulants are materials made on Earth to simulate or replicate the regolith found on the moon to be used in research and testing due to the scarcity and protection of returned lunar samples. The environment on the moon is one of the most challenging that humanity has ever encountered. In addition to extreme temperatures of plus or minus 260 degrees Fahrenheit, one of the most difficult parts of this environment is the nature of the regolith on the moon. Earth's soil contains organic material and particles that are formed by wind-blown and water processes, which makes them relatively round and smooth. The regolith on airless bodies, such as the moon, have no organics, are not altered by moisture, and are formed entirely by impact and explosive processes. This means that these particles are very hard and covered in fractured surfaces with sharp edges, as in the image in the middle. The regolith on the moon is very destructive and hazardous to both humans and technology. It is abrasive like sandpaper and very susceptible to static charge due to its high surface area. Additionally, more than 60% of the regolith on the moon is composed of particles that are quite fine, like those in talcum powder or cake flour. Due to all of these factors, regolith particles easily get into the spacesuit joints or moving mechanisms of rovers and cause them to seize up. Considering how short their missions were, the astronauts' gloves and suits suffered a lot of wear damage. So the Earth is protected from most meteors because they burn up when they enter our atmosphere. Those that do get through radically change the landscape, as in the upper photo, which shows Meteor Crater in Arizona. The moon has no atmosphere, so even tiny micrometeorites hit the surface, making their own little craters that behave just like their larger relatives. This is how rocks on the lunar surface get crushed into a very fine powder. Additionally, the energy of the impact melts some of the surrounding regolith, which then quickly cools and glues other regolith particles together, forming agglutinates, which you can see in that lower left photo. Due to the structure of those agglutinates, they have a significant effect on the mechanical properties of lunar regolith. When you look at the moon, you can see light and dark patches. When Galileo looked through his telescope in 1609, he thought the dark patches looked like smooth bodies of water, which he called mare, an Italian word for ocean. When he studied the lighter portions of the moon, they looked rugged like the mountains on Earth, so he called them the highlands. The soil in the darker colored mare is composed mostly of basalt, as seen in the photo of our mare simulant on the left. The simulant on the right is representative of the lighter highlands, which are mostly composed of rocks called anorthosite. Basalt is very common all over the Earth. However, some terrestrial basalts are going to be a much better match to lunar basalts than others. And Aegean anorthosite is not very common on Earth and is more than 3.5 billion years old. When the Earth was cooling down from a bowl of molten rock, this was some of the first material to float up and solidify on the surface. When you think about the moon, I imagine the view of the moon on the left is the image that comes to mind for most of you. What many people do not realize is how different the far side of the moon looks. There are very few mare patches on the far side of the moon, and while the lunar highlands cover almost 80% of the lunar surface, most lunar missions have landed in the mare regions. And due to communication challenges between the Earth and the far side, only one mission has landed there so far, and it was the Chinese lander in 2019. In this iconic photo of Buzz Aldrin on the left, you'll note how white his suit is, with the exception of a couple dark spots on his knees from a fall. On the right, James Irwin's bottom half is absolutely coated in dark gray regolith. Not only is the regolith abrasive and destructive to fabrics and joints, but the astronauts are susceptible to overheating, as the pristine white design was meant to help reflect heat. I do just want to note how dangerous it is that astronauts like Buzz fall, and yet he was not the only one to do so. Given the nature of the regolith and rocks, falling into a sharp abrasive material could ruin the suit and put the mission and the astronaut's life at risk, especially if they are not near a lander or a habitat. The ability for astronauts to move freely and safely while wearing a suit cannot be overlooked. A new dust-generating system arrived on the moon, starting with Apollo 15 in the form of the Lunar Roving Vehicle. While these LRVs dramatically increased the distance traveled and mission capabilities, they also stirred up even more lunar dust to coat the LRV, the astronauts, and their instruments. In regards to cleaning their suits after each EVA, Gene Cernan said, "Probably the most difficult job of all the closeouts was trying to dust the suits." In the photo on the right, a very dirty Gene Cernan can be seen in the lunar module after taking off his suit. And what I find fascinating about this photo is that Gene was protected from the regolith in his EVA suit. His skin was never exposed to the regolith outside the lunar module. The suits being dirty makes sense, the astronauts inside them less so. And as we can see, despite all the time spent cleaning, the regolith that did enter the lunar module quickly dispersed around the capsule. Many astronauts developed lunar hay fever as a result of breathing in these fine particles. In fact, researchers are now studying how long-term effects of lunar dust might affect the lungs of future astronauts. This table shows some of the statistics of the Apollo EVAs. The 6 missions over 3.5 years show a rapid advancement in the amount of time spent outside the lunar module, the total distance traveled, and the quantity of samples brought back. The addition of the LRV drastically increased the distance covered by the Apollo astronauts and thus the variety of samples brought back. That said, the longest astronauts have spent on the lunar surface is less than 24 hours. If the dust is so abrasive that it wore through 3 layers of Kevlar-like material on Jack Schmidt's boots, how will our technology survive weeks to months on the lunar surface? If you're attending this conference, you likely know that many national agencies and private organizations have visions of a long-term sustainable future and presence on the moon in deeper space. With almost 50 years since the last human mission to the moon, how can we make these visions a reality? NASA's solution is the Artemis program, a series of missions with the goal of landing the first woman and the next man on the moon by 2024. The first phase of this ambitious program will begin with smaller landed missions, transition to larger landers with the deployable rover, and culminate in a crewed mission to the lunar South Pole in 2024. The second phase will build upon the first to increase capabilities for Mars. Normally, industry struggles with bridging the gap between technology and business. Well, still applicable for the space industry, the bigger struggle is going to be bridging the gap between technology designed for environments on Earth and technology designed for the moon and other worlds, of which we often have incomplete or little knowledge. These unknowns are called strategic knowledge gaps, or SKGs, and there are questions that researchers and industry experts try to explain or plan to explain through a mission. One such knowledge gap is dust mitigation. As I mentioned earlier, Apollo-era technology had many issues operating in the dusty environments on the lunar surface, and they just kind of had to live with it. Well, for that vision of humans inhabiting the moon, you can't just live with the dust. We either need to prevent dust from collecting on surfaces in the first place, or we need to create technology that is more durable for this harsh environment. In addition to procedural mitigation techniques, cleaning processes, and strict planning to avoid hazards, Apollo astronauts used dust brushes, dust covers, and rover fenders to reduce or remove dust. Now, the problem with the brush is that it creates static. While the particles are very fine, or with particles that are very fine and susceptible to static charge, these brushes were only marginally effective, as we saw earlier. So, what happens when a vital component breaks on the moon and the closest hardware store is 239,000 miles away? Well, there were several instances of life and mission-threatening breaks during the Apollo mission, but one almost prevented the final 2 lunar roving EVAs of the Apollo era. At the end of the first Apollo 17 EVA, Gene Cernan's hammer caught on the edge of a fender and popped it off. Without that fender extension protecting them from the dust, driving the LRV was a serious hazard. Due to 16G, any lofted dust goes much further than it would on Earth. The astronauts described riding without the fender extension causing massive rooster tails. This lofted dust spread all over their instruments and suits, and since it's darker than the instruments or the astronauts' bright white suits, the dust is absorbing heat from the sun and can quickly start to cause things to overheat. So while the astronauts slept, the team in Houston had to create a replacement fender with only the materials that the astronauts had with them on the moon. Their solution was maps and clamps, as can be seen in that middle photo. This amazing story is going to illustrate the importance of thinking on our feet, adapting technology, and learning from experience how to mitigate dust. Without this fix, the only geologists to set foot on the moon might not have had the opportunity to discover orange glassy regolith on the edge of Shorty Crater during that second EVA. With missions launching soon and both nationally and internationally, new dust mitigation techniques are needed. We need optical systems, advanced fabrics, thermal radiators and painted surfaces, dust-tolerant mechanisms, and new seals and soft goods. As I mentioned earlier, Off-Planet Research is one of the newest SBIR awardees to help advance one of these areas. So let's go back to that vision of the lunar village. We've studied the environment. We've developed new dust mitigation technologies that work great, and we're launching missions on a regular basis. Wonderful. Well, now we need to go back to address the business case we set aside earlier. Science and research goals can only fund so many missions. Governments can only fund so many missions. It would be hard to make the case for a lunar or Martian village without being able to show the financials of why we need to go and not just why we want to go. This is where lunar resources come into play. We need to be able to use the resources of the moon, Mars, and asteroids to literally propel ourselves into deeper space. This all starts with the idea of In-Situ Resource Utilization, or ISRU. ISRU is the idea of living off the land and using the resources around you. There are many resources that can be extracted from regolith and used on the lunar surface. Lunar regolith is at least 40% oxygen by mass, and silicate minerals make up over 90% of the moon. There are a variety of metals and components, that's potassium, rare earth elements, and phosphorus in the regolith as well. And then we have volatiles, which refers to the frozen components that have been discovered in lunar ice. In 2009 LCROSS mission, NASA crashed a satellite into the South Pole and discovered water, carbon dioxide, ammonia, and methane, to name a few, in that ejecta plume. With one data point of ground truth, there are many unknowns for volatiles, but they have revolutionized how lunar resources can be used. Mehdi Benna, a planetary scientist at NASA Goddard, recently measured the content of impact plumes from random meteor impacts on the moon. He told CNN in 2019 that though water is widespread in lunar soil, it is spread very thin. 1 metric ton of water, or 1 metric ton of regolith, yields just 16 ounces of water, which is the amount in an average water bottle. While this may not seem like a lot, remember that before 2009, no one believed there was any water on the moon. And even though the surface of the moon can get as hot as 260 degrees Celsius, a few meters down, the temperature moderates to just above the freezing point of water, which could make things interesting. Also, for scale, the sacks contain about 1 ton of crushed rock. What makes the ice in permanently shadowed regions, on the other hand, so attractive is that there is expected to be a lot more water per ton. The LCROSS observations indicate more than 5% of the material in the PSRs is water ice, with some other ices mixed in, as I mentioned before. And that's going to be about 15 gallons of water per ton of regolith. And that is what makes polar mining so interesting and so attractive for a lot of organizations. Now, I'm not going to answer this question, but I will pose it. The question is going to become then, what is going to be more feasible? Excavating tons of dusty, abrasive regolith in the sunlit regions for smaller quantities of water, or potentially extracting larger quantities of water on or near a surface that is extremely cold and extremely dark. Other things to consider are going to be the ice composition, its formation heritage, and physical properties, and how that might affect the processing or collection. And also keep in mind that lunar regolith is very dense and cohesive, and either way, it is not going to be easy to move. Let's go back to the good byproducts. So we mentioned earlier, oxygen and hydrogen, they can be used in rocket fuel, breathable air, drinking water, and agriculture. The rare earth elements that are in their unrefined state on the moon can be exported back to Earth to be used in many applications, like electronics. Raw or processed regolith can be used in sintering or 3D printing applications to make tools, construct buildings, and protective thermal and impact shields, and roads. Earlier, I mentioned that there are a lot of unknowns about volatiles found in the polar regions. Again, the largest supply of volatiles that is most easily accessible is going to be, or accessible from the surface, is going to be in those permanently shadowed regions where the sunlight never hits. These regions at the North and South Pole are often in or at the edge of craters and are ultra cold at minus 260 degrees Fahrenheit, Celsius, or colder. And depending on the crater, you're going to have some access issues as well, getting in and out. Early missions to those polar regions are going to need to send prospecting instruments and rovers, like NASA's Viper rover, to head into these extreme access environments to categorize and map the distribution of volatiles in preparation for future excavation and extraction missions. Later missions can utilize those resources to create a robust infrastructure on the surface. So back to the business case. In order for ISRU, and particularly lunar rocket fuel, to make sense financially, it needs to be less expensive to source propellant from the moon than to launch it from Earth, and there needs to be a market. With the recent flurry of mission planning to the moon and deeper space by the commercial industry and national and international government agencies, the market has mostly been defined. The biggest delta V is getting out of Earth's atmosphere. Once you're out of LEO, the delta V significantly reduces and each kilogram of propellant becomes more efficient. If the cost of propellant obtained from the moon in low Earth orbit or LEO is less than the cost to ship the propellant to LEO from, to ship the propellant from LEO to Earth, then the business case can be closed. Refueling the upper stages in LEO can transport heavy payloads from LEO to GEO and beyond. And this can increase the affordability of NASA's activities on the moon, ESA's Moon Village, and missions to Mars and other places in deep space. While the savings depend on the in-space transportation approach and assumptions, there is a business case that can be made for sourcing propellant in space. I know other presenters have spoken more about that, so I will refer you to them for more specifics. But just to drive it home, a 2019 WGM report released a conceptual economic study on mining water on the moon, and they see the market as encompassing satellite refueling, International Space Station and Lunar Gateway, Moon and Mars bases, space agriculture, and tourism and hotels. They're valuing this market at $206 billion over the next 30 years. The moon is a stepping stone to the rest of the universe, but it should not be overlooked for the science and resources that it offers in its own rights. By developing lunar resources, colonizing space becomes more profitable and desirable. Regolith, which is one of the biggest nuisances and hazards of the moon, just might be the very reason that humanity can envision a thriving economy in space. Ultimately, the reason for becoming a multi-planet civilization is to better the lives of everyone and ensure the survival of humanity. As we begin the next stage of space development, we need to ensure that we work to make this vision a reality while not repeating the errors of our past. And learning to survive and thrive on the moon is our first step towards this new existence. In the future, there will be thousands of people hopefully working and living in space. This is the beginning of the next great human adventure. And on that happy note, thank you for your time, and I welcome any questions.
Right on, Melissa. Thank you very much. In the awareness of time, we've only got about 6 minutes, so we're gonna tackle this quickly. I got a couple kudos from you from the audience. I just want to pass that along. Also, your conversations about the business case closing with some of those plans, right? That whether that's rocket fuel or rare earth or elements. But let's be really clear. That's not what you're doing now, right? What you're doing now is much more mundane, frankly, more down to earth, and frankly, a better business model, right? So let's talk about what you're doing now to enable that larger infrastructure that's envisioned, right? So what is the piece that you provide?
Yeah, definitely. And so as I mentioned earlier, there aren't a lot of lunar resources that were brought back for the moon, and they're very well protected because I know there's a lot of people, if they could, they want to get their hands on actual lunar regolith. That is the goal, right? Well, for a lot of researchers, they're never going to be able to do that, especially if it is a destructive process, which especially if we're talking about lunar resources, any processing method is going to be destructive. And so you need to look for alternatives, and that's where stimulants come in. And so what we decided to do, given our own interests in space, in particular the moon, was to create the type of testing materials that we ourselves want to use. And that's where we came up with our lunar regolith stimulants and the variety of types and compositions that we offer. And we really want to be able to enable researchers, everything from agricultural research to testing a rover, to testing remote sensing instruments, to testing ISRU extraction, to be able to offer them a stimulant that is going to work for them and their specific needs. Because all of those different organizations might have different specifications or standards that they're going to need and have different focuses on what's going to be most important to them. So we really like to work with these organizations to make sure they're getting a good representative test material for their specific use. Michael, you're muted.
Most of a year in a pandemic, and I still can't figure out when to turn the button on and off. So would it be fair to say that you're one of the levers that help the folks that are helping everybody else? Like they can't do the work that they want to do unless they start with in-lab testing, whether it's from your simulant or some other, some other source, right?
You said it, not me, but yes, we do kind of view testing. We're engineers by degree and by trade. We view testing as vital to the success of the technology and the mission. We need to be able to prove it's going to work, and it's going to work as expected. In order to have, missions, future missions approved, it goes a little bit better when the first one was successful and met its mission objectives. And so what we want to be able to do is help, again, enable long-term research and development, and you're going to need consistent test materials in order to do that.
Well, and by building the, I'm going to say dirt, I know you don't think that's the correct response. By building the regolith and becoming the folks that get really, really good at understanding regolith, doesn't that also put you in a really interesting position when those ultimate larger, longer term markets become available?
Yeah, I mean, we like to say we work with Lunar regolith stimulant every single day. We've seen it destroy our own equipment and had to quickly learn to adapt how we operate and how we have moving mechanisms. And so we want to harness that knowledge. And so we do provide consulting. And then we also are using the knowledge, as I mentioned, to develop our own hardware, starting with dust tolerant fluid and gas connectors.
So during the course of the last couple of days, we've had companies that were billion-dollar valuations. We've had companies that recently got purchased, 2 different companies that got recently purchased for a couple $100 million. Where are y'all in the ecosystem?
We are a small semi-startup company. We're now 5 years old, but we spent quite a long time in research and development, about 2.5 years in research and development, to ensure that the products we were putting out there were, again, ones that we were proud of and happy with and could back up with data and knowledge. And so we still like to call ourselves a fairly young startup company. So we're definitely on the smaller side. We're one of those little companies who's very thankful for the grants that we have been able to get that help advance the goals that we want to have.
Cool. I mean, we all know that research is a necessary precursor to all this work. So I want to thank you for your time and your presentation. It was, I think it's a necessary reality check for where we actually are. It's nice to see where we're going, but this whole conference is about where we are today to enable the next thing. So thank you very much. We're going to move it on to Lila. Thanks a lot. Melissa, make sure you put your contact information down there. There were some folks that were interested in your slides. If you're willing to share those, let us know.
Yeah, I'll start responding to some people in the chat.
Thanks.
Thank you, Michael. Thank you, Melissa.